From today, we just started learning the basics of the different chapters of mathematics. In this video, we will study about the chapter 1 of the class 10 mathematics, that is the real number. That is real number. In this chapter, we will know about the different aspects of real number and what are the main topics which want to cover in the basics of real number. So let's start the video. In this video we will know about the Euclid division lemma, fundamental theorem of arithmetic and the irrational numbers. In this video we will first know about the Euclid division lemma. Okay, let's change the color of the pen. Euclid division lemma, and the second one is Euclid division algorithm. In Euclid division lemma, state and apply the lemma for any pair of positive integers. And the Euclid division algorithm, it is used for the find HCF of two numbers using successive division. And the third one is the fundamental theorem of arithmetic, express numbers as unique products of prime numbers. And the fourth one is irrational numbers, such as root 2, root 3, root 5 are the irrational numbers. In root 2, root 3 and root 5 are the irrational numbers. In this we can prove the root 2, root 3 and root 5 are the irrational numbers. And the fifth one is decimal expansions. Distinguish terminating and non-terminating recurring decimals. In this decimal expansion we know about the different types of decimal expansion, such as the non-terminating recurring decimals. And the last one is the HCF and LCM applications. Next, the first one is Euclid lemma, second one is division algorithm, and third one is FTA, prime factorization, and fourth one is LCM and HCF using prime numbers, and fourth one is irrational numbers, proof techniques, and the fifth one is decimal and terminating recurring numbers. Next one, we already know about the rational numbers, real numbers, rational numbers, integers and the whole numbers and natural numbers. And irrational numbers, as some of the examples are root 2, root 3, pi and e. Its examples are also non-terminating, non-repeating decimals. These are the examples of irrational numbers. Let's start the Euclid division lemma. Euclid division lemma states that the given any two positive integer a and b, there exists unique integer q and r such that a is equal to bq plus r, where 0 is less than equal to r is less than b. In this, the dividend is a, the number is being divided is a, and the divisor in this is small b, the number we divide by, and quotient and remainder are small q and small r. In Euclid division algorithm, we will study the systematic method to find the HCF of the positive two integers. Apply lemma, write a equal to bq plus r with a is less than equal to r less than b. Replace if r is not equal to 0, then replace a by b and b by r. Repeat, continue until the remainder becomes 0. The last non-zero remainder is the HCF of a and b, the two integers. Next slide. Let's example by using the Euclid algorithm we can find the HCF of the 455 and 42. So let's break down the 455, 42 into 10 plus 35. R is equal to 35, that is not equal to 0. Again replace 42 is come here and the 35 is come here. So 42 is equal to 35 into 1 plus 7, and next step, this step is here and next step is here, and this 7 is here, and this 35 is here. This is the Euclid algorithm rule. and 35 is equal to 7 into 5 plus 0, that means r is equal to 0. So in this we can stop the Euclid algorithm, and the HCF of the 4, 55 and 42 is the 7, that is given here. Next topic is the fundamental theorem of arithmetic. Every composite number can be expressed as the product of primes, and this factorization is unique apart from the order of the prime factorization. This is the fundamental theorem of arithmetics. Existence, whenever it exists, every composite has at least one prime factorization. Every composite has at least one prime factorization. Uniqueness, the factorization is unique up to order of factors. Primes, building blocks, all natural numbers greater than 1. There are the numbers which are the factorized by the product of primes. The examples are 60, 140, 2310 and 1008. Let's example of a 60. 60, after the breakdown of a 60, 2, 30, 2, 15, 3 and 5. So after breakdown we can write that 2 to the power 2 into 3 into 5 as a full expression of a 60. Similar way 2310 we can write that 2 into 3 into 5 into 7 into 11. Similarly 140 can be write that 2 to the power square into 5 into 7, and 1008 it can be also written as a 2 to the power 4 into 3 square into 7. This is the final expression in the form of a product of primes. Next slide. Finding HCF using, in this slide we will know about the how to find the HCF of the given numbers using the prime factorizations. Let's say example HCF 60 and 140. 60, after the prime factorizations we got the prime factors of 2 to the power 2 into 3 into 5 after breakdown of the 60, and after breakdown of a 140 we can find that 2 square into 5 into 7 to the power 1. The common primes are 2 square into 5 to the power 1, hence the HCF is this 2 square into 5 is equal to 20. Let's another example using the prime factorization 60 and 140. So after breakdown we can 60 write that 2 square into 3 into 5. 140 can be written as 2 square into 5 into 7 to the power 1. All primes highest power are the 2 square into 3 into 5 to the power 1 into 7 to the power 1, that is the LCM. In this slide we can calculate the LCM, and in the previous slide we can calculate the HCF. Always remind fundamental relation, the HCF and LCM, if the two numbers are given, then HCF and LCM of the two numbers are given, then it is equal to the product of two numbers. It is a fundamental relation, such as HCF of 60 and 140 is equal to 20 and LCM is 420. If both multiply, 20 and 420 is equal to 8400, that is equal to the 60 into 140. Verified. Irrational numbers. Irrational numbers are the numbers which cannot be expressed in the form of p by q, where p and q are the integers and q is not equal to 0. Irrational numbers are the numbers in which we can express any number in the form of p by q, and the q cannot be 0, such as root 2. Root 2 is a rational number. After putting the value of root 2, we can find that 1.414213, it is non-terminating, non-repeating, and the root 3 value 1.732050, it is non-terminating, non-repeating. Similar, root 5 value is 2.236067, non-terminating, non-repeating. Pi value of pi is 3.141597, it is transcendental irrational number, irrational, that is the value of pi. And after that the conclusion of a irrational numbers or root 2 is a irrational number. Assume that is a contrary. Suppose root 2 is a rational number, then root 2 is can be represented in the form of p by q, squaring both sides. 2 is equal to p square by q square. If p square is even, then p is also even. Let's p is equal to 2k, then squaring 2k square is equal to 2q square. 4k square is equal to 2q square is equal to q square is equal to 2k square. So q is even. Both p and q are even. The GCD, greatest common GCD that of p and q is greater than equal to 2. Contradictory GCD is equal to 1. So our assumption is false, hence root 2 is a irrational number. Let's some example of a terminating decimal expansion and a non-terminating decimal expansion. Terminating decimal examples are 1 by 2, 3 by 4, 7 by 8 and 1 by 5. These are the terminating decimal expansion. In this, decimal ends after the finite digits. Terminating decimal expansion are the decimal expansion after finite digits. That means the after some division it got ends. And non-terminating recurring, that means digits repeated indefinitely. 1 by 3, that means 0.333, it can be written as 0.3 to the bar. 2 by 11, 0.1818, it can be written as 0.18 to the power bar. 5 by 6, 0.83 bar. Sometimes it can be 1 by 7, it can be written as 0.14285, 7 to the power bar. Theorem of a terminating decimal expansion. There is a theorem existing in the theorem of terminating decimal expansion. Let p by q is a rational number in the lowest terms, and let x as the terminating decimal expansion if and only if the prime factorization of a q in the form of 2 power m into 5 to the power n, m and n both are greater than or equal to 0. Example 7 by 8, 8 is equal to 2 to the power cube terminating. 13 by 15, 25 is equal to 5 to the power square terminating. 17 by 40, that means 40 by 2 to the power 3 into 5, that means terminating. 11 by 30, so 30 is equal to 2 into 3 into 5, that is non-terminating, has 3, hence it is a non-terminating. If 2 and 5 are present, then it is always terminating. You can see the examples here. In this the slide, decimal is a non-terminating recurring. Just examples 1 by 3. In the previous slide we can discuss these topics. 0.3 and above the 3 the bar is present. 2 by 7, 0.285714, denom is 7, here denom is 3, here denom is, and 5 by 6 is equal to 0.83 to the power में bar, 0.09 up to bar, denom 11. 4 by 11, 0.26 to the power bar, here denom is 3 into 5. Chapter at a glance. In this chapter we will study about the Euclid division lemma in a very short way, and next one is the fundamental theorem, and another one is the irrationality of the root p. Any number we can know about the irrational, how can, and we can prove as a contradiction method. Euclid algorithm, we can find the HCF by interchanging the a with b and b with r. HCF and LCM is equal to the product of number. In this video we will know about the briefly, and the terminating and non-terminating decimals. If you are free and try to learn something new, then use Euclid division algorithm to find HCF. Express 156 as a product of primes. Find HCF and LCM of 12, 15 and 21 using prime factorization. Prove that root 5 is irrational. Without actual division, whether 13 by 3125 has a terminating decimal, it can be checked. Write the decimal expansion of 17 by 8 and 5 by 13 without long division. And the next one is, thank you for us in the chapter 1 real number, that is the master of lemmas, and prove that irrational numbers own the decimals. Practice daily and revision theorems and solve NCERT questions regularly. For more video